Yeah, chemical equilibrium, chemical equilibrium, chemical equilibrium. Oh, yes, yeah. It's one of the most important topics in chemistry, and it's important that you understand the concept. So we'll be using a couple of hours or minutes, depending on how fast you could be, to explain chemical equilibrium. I'll be explaining it at a very basic level. Now, you can understand. Okay. So, okay. If you are here, please drop a comment. Let me know. Let me know. Let me know. If you can see my screen, if you can see my screen, let me know. If you can see my screen, let me know. If you can see my screen, let me know. If you can see my screen, let me know. Okay. If you can see my screen, let me know. Drop a comment, please. Only one person is here. I can only see. Okay, good. If you can see my page, drop a comment. Yes, I can see. Fantastic. Yes, I can see. Good. Isaac Newsroom can see. 5 people are here. I'm just seeing 2 comments. Drop a comment. Let me know. Tilda, can you see my screen? If you can see my screen, just drop yes, so that we can continue. You can see my screen. Good. Good. So let's get into work. Can you see my screen? Just drop yes, not I. Just drop yes. Good. If at any point you cannot hear me, let me know. Okay. So let's get into work. Now, yes, yeah. Yes, sir. Good. Now, chemical equilibrium, right? It's just basically 2 things, right? It's just chemical and equilibrium. That's what it means. And it's just 2 things: chemical and equilibrium, right? That means this chemical here, we are talking about chemical reaction that are what? That are equal. I know it might look basic. Yes, that's just it. It's basic things. It's just chemical reaction that are equal. So when we talk about chemical equilibrium, is a form of dynamic equilibrium in which see, there's no cramming here. You understand it very well. In which the rate of forward reaction is equal to the rate of backward reaction. Now, I'll be giving you some tips and everything to understand this thing. So, the rate of forward reaction is equal to the rate of what? Backward reaction. It's as simple as that. It's basic like that. So, now what am I trying to say? That means if we say chemical reactions, there must always be a chemical equilibrium. There must always be a chemical reaction in which it is in equilibrium. Now, I want to ask you a question. Are you trying to say, will there be something called physical equilibrium? Will there be something called physical equilibrium whereby there's nothing like a physical change? There's nothing like a physical change. Sorry, there's nothing like a chemical change. Just physical change happening, and that reaction is in equilibrium. Yes, there is. I'll give you an example. Let's say Tilda when she was in primary school, that seesaw that you guys do, Tilda is here and Zacchaeus is here, right? Now, if Tilda weighs 50 kilogram and Zacchaeus weighs 50 kilogram, yes, they are equal. That is why they will be balanced, right? They are equal. But because in this kind of thing, there's nothing like a chemical change. It's just physical balance. So in this kind of thing, we say these guys are in physical equilibrium. We say they are in what? In physical equilibrium. Because There's nothing like a chemical change. Just two bodies, right, on a seesaw. 50 kilogram, 50 kilogram. Nobody is cheating anybody. They are just in equilibrium, right? Now, another very fantastic example of physical equilibrium is when you are making a atom, right? If you are making a atom, two things is actually happening. Two things is happening. If you are making a atom, two things is happening. Two things is happening. Now, what is happening? If you are making eba, dissolution of the garri, making eba, dissolution of the garri inside the hot water, and precipitation. Precipitation. That means two things is happening at the same time. But don't forget, the eba is still garri and water. So there's nothing like a chemical change. So in this case, it's still a physical equilibrium. It's still a physical equilibrium. Right? That means the question now becomes, can you guys hear me? I want to be sure. Can you guys hear me? Can you guys hear me? Can you guys hear me? I want you guys to type yes on in the comment section. Good. 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 So the solution of the garri and precipitation is happening at the same time. That's why the garri quantity tends to increase, because the garri will precipitate. Abi? So it is also a form of physical equilibrium. The solution, garri, if you are making a bathroom now, you have hot water, you are pouring garri inside, it will be dissolving now, the solution, and at the same time there will be precipitation. That's why the garri quantity, the eba quantity will be more than in a way. So they are in equilibrium because the solution and precipitation is happening at the same time. Okay, these two processes is happening at the same time. They are in equilibrium, but there's no chemical change, so we call it physical equilibrium. Okay, that is that. Now the question becomes, if we understand that it is only chemical reactions that can undergo chemical equilibrium, right? Because we already said if it is a physical change, it will be physical equilibrium. Now the question becomes, will all chemical reactions undergo chemical equilibrium? That's the big question. Will all chemical reactions undergo chemical equilibrium? That's the big question. Now we will find out if this is correct. We will find out. Now this question now leads us to the next phase of our teaching, which is what? Factors. This question, yes, please be screenshotting. Oh, be screenshotting. Be screenshotting, just so that you don't delay us. There's no time. Screenshot. What is no? I think Zacchaeus, what is no? I didn't get that. Screenshot. Then screenshot if you want to. So now, will all chemical, okay, I get what you're saying. Will all chemical reaction undergo chemical equilibrium? Yes. The answer, you will now know the answer if it is a no or yes. Yes or no. Don't answer yet. You will now know. So now the next thing now becomes factors necessary for chemical reaction to be in chemical equilibrium. Factors necessary for chemical reaction to be in chemical equilibrium. That is, we've already established the fact that there must be a chemical reaction for it to have chemical equilibrium. Now, what is now the factor responsible for that thing to happen? Now, that means that reaction, number one, the reaction must be reversible. It must be reversible. We have factors necessary for chemical reaction to be in chemical equilibrium. Number one, it must be reversible. Please underline the word must be. Number two, it must be in a closed system. It must be in a closed system. Look at it. I did not say it may. What did I say? It is a must. Number 3, the rate of forward reaction must be equal to the rate of backward reaction. Right? Now, these are the major 3. Now, they can add another one for you. And I know that you must have heard it. They will tell you that the Gibbs free energy, you must know this one because I have to add it. The Gibbs free energy must be equal to 0 for a reaction to be in chemical equilibrium. You would have seen that when they say change in G equals to 0. Change in G equals to 0. If the reaction is spontaneous, change in G must be less than 0. If the reaction is not spontaneous, change in G must be greater than 0. But if the reaction is in chemical equilibrium, change in G, that is change in G's free energy, must be equal to 0. Now let's pick them one by one. You will now see what I meant by that statement. Look, don't forget this. It is important. Screenshot if you want to. It must be reversible. Now, I mean, yes, we already understand the fact that there must be a chemical reaction, right? Now, we are not saying that for that reaction to be in chemical equilibrium, these things must happen. That's why I told you that means if a reaction does not obey these things, it is not in chemical equilibrium, despite the fact that it is in despite the fact that it is a chemical reaction. Okay, so it must be reversible. It must be in a closed system. The rate of forward reaction must be equal to the rate of backward reaction. Then Gibbs free energy must be equal to 0. Take note of this. It's very, very important. JAMB question. This is a JAMB question on its own. They will just tell you which of this is not a factor or is not necessary for a particular reaction to be in chemical equilibrium. A, it must be reversible. B, it must be in a closed system. C, the rate of forward reaction must be equal to the rate of backward reaction. D, it must be in an open system. The answer is open system. Open system is not a condition for a reaction to be in chemical equilibrium. Okay, now let's deal with it one by one. Number one, it must be reversible. Absolutely. I mean, how will you be in chemical equilibrium if you are not reversible? Look at it. Let's say, for instance, we have CaCO3. Don't forget, I used to tell you, this CaCO3 represents 3 things. It represents limestone, it represents chalk, and it represents what? Marble. Don't ever forget this thing. This calcium triosocarbonate 4. Calcium triosocarbonate 4. So let's say this guy just undergo thermal reaction whereby there's heat and it forms CaO and CO2. You would agree with me that this is actually a chemical reaction, but this thing can never and will never be in chemical equilibrium. Why? It is a complete single reaction, and a complete single reaction will never be in chemical. You will know why. It will never be in chemical reaction. But let's say we have CaCO3 going to CaO and CO2, and at the same time this CaO and CO2 is combining to form this guy. Okay, this CaO and CO2 is combining to form this guy, so that this reversibility sign is there. Hence, absolutely, we can say that this reaction can be in chemical equilibrium, despite the fact that it is a chemical reaction. So now, that's why I asked that big question. Now, go. I'm not going to tell you to answer yet. Look at it again. This is a chemical reaction, but it is not in chemical equilibrium. Why? There is no reversibility. That's why reversibility sign is a condition. Number one. That's number one. Number two. Are we good? Are we good? Do you get it? Do you get up to this point? Do we get up to this point? Number one condition, it must be reversible. And I use this to explain that. Do we get up to this point? Do we get it up to this point? Yes, sir. Good, 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 good. Now let's continue. Good. Number 2, it must be in a closed system. Where exactly? Aminat, where don't you get? Don't always, please, if you don't get something, just talk so that I can emphasize it again. I cannot know, I just have to ask you. Always talk. So I will emphasize, I will talk about it again. It must be in a closed system. Closed system. I will tell you what it means by closed system. And before that, I will tell you what a system is. What is a system? What is a system? This is not computer system now. System in chemistry or physics. A system is a place in the universe, set aside for the purpose of an experiment. Sir, we are done with water. No, it must be a new topic. We are not done with water. We are done with water. Solution and solubility is the next thing. This must be a new topic because it's live. So, system is a place set aside in the universe for the purpose of an experiment. System is a place that means this place can be a system. Your kitchen can be a system. Any place can be a system because so far it is set aside for the purpose of an experiment. It is a system. Now, there are 3 types of system. There's an open system. I will not dwell much on this. Closed system and isolated system. These are the 3 types for physics. You must know this. Open system, closed system, and isolated system. These are the 3 types of system that we have. Now, but the one that is responsible for chemical equilibrium, you are doing well, the chemistry talk. Yeah, thank you so much, my chief. That's bright. Now, this system that is responsible for chemical equilibrium is that it must be closed system, right? I will tell you, it must be closed system, not an open system, not an isolated system. It must be a closed system, and I will tell you what it means. Now, imagine you are inside your room right now, and the door of your room is closed. Imagine like that is a system. You know, your room can be a system. I already told you. Imagine you are inside your room. Just imagine, I know most of you are inside your room now, and the door of your room is closed, right? Now, let me ask, can anybody enter? Can anybody enter that your room? Closed system now, because it's what is important here. Can anybody enter your room because it is closed? Can anybody enter? Can anybody enter your room because you closed it now? I'm not talking about abnormal situation now. The door of your room is closed. Can anybody enter? Can you leave? No, until they open it. No. Yes, good. Nobody can enter, nobody can leave until you decide to open it. Right? That means after 5 minutes or 5 hours, the change in M will actually be equal to 0. Why? Because what you start with, if you have 10 people in your room before you close it, after 5 minutes, it is still 10 people that will be there. So M2 minus M1, which is change in M, will be equal to 0. Now, the fact that you are inside your room closed does not mean you cannot exchange blow. Does not mean you cannot cook inside your room. Does not mean you cannot fight. That means the change in energy will never be equal to 0 because you can exchange energy. Because you can fight. Because your room is closed, we already established the fact that people that started are the people that will finish. But in a case where energy, now this is energy, you can exchange it. You can heat up your gas. You can start cooking. Sun can enter because even though your room is closed, it can enter through the roof. So change in energy will never be equal to 0 because there will be change in energy. This change you are seeing here, this change in M now means M2 minus M1. This change in E means E2 minus E1. Now, what does M stand for? Matter or mass? M stand for mass or matter. M stands for mass or matter. Okay, now if you understand this concept, now this is trivial example. Let's now take it back to chemistry and now see why it is important for chemical equilibrium. I need to build this concept so that you're able to understand what it means. M stands for matter or mass. E stands for energy. E stands for energy. Now let's take it back to chemistry. Let's take it back to chemistry. Now, we know we are still on closed system. Now, if you understand what I said, look at it. Let's now use it for this guy. CaCO3. It has obeyed the first rule. It must be reversible. We already said that. To form CaO and CO2, right? Good. Now, CaCO3 and CO3. Imagine that this CaO and CO2 is allowed to escape, such that these guys are not in a closed system whereby the door, I'm using door now, the door that you are making this reaction is not opened. Imagine, or you go and imagine this guy is allowed to escape. Do you think with this CaO and CO2 be able to combine to form CaCO3? The answer is no, because you have allowed CO2 that is a gas to escape. You have allowed CO2 that is a gas to escape. It will not be in equilibrium again. Can you see why closed system is a must? Is a must, such that you can only eat it. You know, I told you that energy can be exchanged. You can only eat this reaction with it. You can only eat it so that it forms CaO and CO2, and it must happen in a closed system so that this CO2 is not allowed to escape. Do you get this now? Do you get M stands for matter or mass? Yes. Do you get why it must be in a closed system? Because we already said that for chemical equilibrium, the rate of forward reaction must be equal to the rate of backward reaction. But if you allow CO2 to go, what will combine with CaO to form CaCO3? Do you get that? Do you get why it is a must that it must be in a closed system, such that this CO2 is not allowed to escape? Do you get the second condition? Do you get the second condition now? Do you get the second condition? Do you get the second condition? I want you guys to always type. Oh, if you don't type, I will not know. Always type, please. Good, fantastic. Ishola, he said no. Closed system means you don't allow this gas to escape. That's what it means. Such that CaO and CO2 can combine together to form CaCO3, because we already established the fact that they are equal. And for them to be equal, the rate at which this guy is decomposing to form CaO and CO2 must be the same rate at which CaO and CO2 is combining to form CaCO3. That's what it means. That's what it means. So, because if you allow this guy to escape, CO2 will escape. Chemical equilibrium. Those of you that just joined, chemical equilibrium. You can watch the I will make the recording available. So let's get in. Now that is that. Number 3. We said the rate of forward reaction must be equal to the rate of backward reaction. See, I will use something to explain this now. That's the third. See, don't forget, I'm putting it is a must. It's not that it's anyhow. It is a must that this must happen. The rate of forward reaction must be equal to the rate of what? Backward reaction. It is a must. Now I will teach you. Now look at what happens. Right? Now imagine this. I will use a trivial example before I use in burning air. Can we say it is an open system? Absolutely. That one cannot even undergo chemical equilibrium in this case. It is open. You are burning that one in air. Air is the product are escaping. That's not what we are trying to talk here. But yeah, that's true. Now let me use a trivial example. Imagine you are in a room. Imagine you are in a room and you are about, let's say, 1,000. You are about 1,000 in this room, 1,000 people. And I asked you guys, oh, you guys, oh yeah, start, Tilda should lead. Tilda, start moving out. And I asked you guys to move out. Please, I'm using a trivial example first, though, so that you understand. And I told you that immediately you get to this point B, this point B, turn back and move back into the room. Look at it, oh. Immediately you get to this point B, you know, Tilda is still leading. Tilda will just turn back and start moving back into the room. I know why I'm using this example. Tilda will just move back and start moving inside the room. Now, let me ask you a question. You know you have about 1,000, right? Do you think the 1,000 person would have moved out before Tilda start entering? I don't need, if even if you don't say the answer is no. Because they are just how many people? No, it is no. Look at it. They are just 1, 2, 3, 4, 5, 6. They are just 6. It's just the 6th person here that is outside before Tilda turns back and start moving inside. Look at, it's just 6 person that is outside before Tilda turns back and start moving inside. So what it means is that you should not exhaust the old people that is inside before the first person starts coming inside. Look at it. There are 1,000 people inside. You should not exhaust this 1,000 before this guy, Tilda, which is the number 1, moves into the room. Now, this is a trivial example. Let's go back to chemistry. Now, let's say we have CaCO3, which is forming CaO and CO2. Now, what the rate of forward reaction must be equal to the rate of backward reaction. What it means is that the rate at which this guy is decomposing with it and forming CaO, calcium oxide. Please note, JAMB question. Calcium oxide is a drying agent for ammonia. It's a JAMB question. Drying agent for ammonia. That's a JAMB question. Calcium oxide is a drying agent for ammonia. They call it quick lime. There's a reason why they call it quick lime. It is fast. It is fast. That's why they call it quick lime. But that's by the way. I don't want to explain carbonation, you know, and all of those things. The process of slaked lime, slaking of lime and all that. But just know, it's called quick lime and it's a drying agent for ammonia. It's a JAMB question. Now, let's get back. Now, what this statement means is that the rate at which CaCO3 is combining, is decomposing, should be equal to the rate at which CaO and CO2 is combining to form CaCO3. What it means is that CaCO3 should not finish before CaO and CO2 combines to form CaCO3. So what's the difference between quick lime, slake lime, and soda ash? They are different things, right? This is quick lime. This is slake lime. Solid, right? Lime water is when you dissolve this one in water. That's when it becomes CaOH aqueous. I don't want to scatter this stuff. Just know that this is quick lime, calcium oxide. Slake lime is calcium oxide solid. Lime water is calcium oxide in water, aqueous. So now let's I don't want to divide this class. I just want to say that because I mentioned it. Now, the rate at which calcium carbonate is decomposing must be equal to the rate at which CaO and CO2 is combining together to form calcium oxide. That is what this statement means. Now, that's what it means, that you should not finish the people inside this place before Tilda, who is the first person, moves back into the room. Because if you exhaust this one, they will not be in equilibrium again. They will not be in equilibrium again. If you exhaust this guy before this guy combine to form this guy, they will not be in equilibrium again. Do you get this third statement now? Do you get this third statement? Do you get that third statement? Good, good, good. Now let's move. Please, so don't ever forget these three things. If you don't remember these three things, don't go and write the exam. It must be reversible. Factor the energy for equilibrium reaction to be chemical equilibrium. It must be reversible. It must be in a closed system. The rate of forward reaction must be equal to the rate of backward reaction. This one is an addendum actually. The Gibbs free energy must be equal to 0. God. Now let's go back to our question. Now the question is, will all chemical reaction undergo chemical equilibrium? That's the question. Is it yes or no? Is it a yes or no? Will all chemical reactions undergo chemical equilibrium? Is it yes or no? No. Fantastic girl. I love you guys so much. The answer is no. Not all of them until they meet this condition. Until they meet this condition, that's when they can undergo chemical equilibrium. Until they meet, that's why it is a must. Until they meet this condition, that is why they can undergo chemical equilibrium. Okay, now let's go. It's not yeah, it's no. Until they meet this condition. Once they meet this condition, they will undergo. But if they don't meet this condition, they look at this guy now. Look at this guy. This is a chemical reaction, but it's not in chemical equilibrium. Because why? It does not meet the reversibility sign. It's not there. Okay. Now let's now go to okay. Let's move ahead. Afusa, do you get that now? Let's go. Now we have explained that those factors responsible for chemical equilibrium to be in, chemical reactions and all of that. So now let's get to equilibrium constant. Equilibrium. See, this thing is one of the most important thing in this topic. Equilibrium constant. Okay. Equilibrium constant this thing is very, very important. Now, please note, we can have K, right? We can have KC and we can have KP. Now, this just means equilibrium constant. Okay, and this KC, because there is C here, it means equilibrium constant for concentration, because of the C, for concentration. Why this KP is equilibrium constant for pressure? Equilibrium constant for pressure. Some people say partial pressure. So the third factor is a bit confusing for most of us. You speak for yourself. You don't speak for other people. You speak for yourself. The rate of forward reaction must be equal to the rate of backward reaction. The rate of forward reaction must be equal to the rate of backward. It's simple. You should not exhaust the reactant before the product combines to form the reactant. It must be the same time. It must be happening at the same time. CaCO3 should decompose to form CaO and CO2. CaO and CO2 should combine to form CaCO3 at the same time. That's what it means. It's an English word. The rate at which forward reaction, the rate at which CaCO3 is forming CaO and CO2. This backward reaction, CaO and CO2 should be able to combine together to form CaCO3. That's what it means. There's no hard and fast truth to it. It's just an English word. So let's continue. Now, before this thing, to know it, you just have to understand that K, to write equilibrium constant K, it just means these two brackets, it means the concentration of the product over the concentration of the reactant. That's what it means. Okay. Yes. Some texts will call it KEQ. Yes. KEQ. Yes. I know. But most of the time, JAMB don't use that. But if they use it, good. But that's why I'm trying to give you this. Now, this thing that you are seeing, right, as you can see it, is the product over reactant. But if you want to write KC, That is where this thing. Now note. This is the most important thing. What is no? What is yes? Note. You have to tell me what is no, what is yes. I don't know what you mean. Note. Should I write it here? Will it contain it? Okay, let me just write it. To write for Kp, don't forget, pressure only affects gases. Pressure only affects gases. So to write for Kp, we consider gases only. See, this is the major myth of this matter. We consider gases only. What is known now? What is known? To write for Kc, this is where the matter. We consider gases and dissolved species. That means, when I mean dissolved, I mean aqueous. That's what I mean by dissolved species. Now, from here, you can say something. What can you say? We don't consider solid and liquid. Please screenshot if you want to screenshot this before I move on. See, if you know this, you can write any equilibrium constant. I bet it with you. You can do it. Now, the next thing is, the last one, the last note you should note. We don't consider solid and liquid. We don't consider solid and liquid. Gases are the, yes. That's what I said. Gas for KCO. I know what I'm saying. For Kc, gases are dissolved species. This dissolved species here, we are talking about aqueous solution. But for Kp, because pressure only affects gases, we consider gases only. Okay, gases only. Now, if you are writing equilibrium constant, we don't consider solid and liquid. Now let's delve into it. Let's delve into it. But before I move on, okay, I will say it now. Let's delve into it. Consider this reaction. A into gas plus B into solid. There's a coefficient B to give C into C. Let's say aqueous. Then D into D, let's say gas. Now, A, write the Kp, 2, write the Kc. Now, if they tell you, if they don't indicate Kp or Kc, and they don't say write the equilibrium constant, they also mean Kc. If they don't indicate, if they mean Kc. Yeah, let's do it. Now, let's go. You will see it now. Solution. Now, Kp, what did I tell you that we consider? What do we consider? Because pressure only affects gases. You don't see it clearly, okay? Can you see it now? Can you see it now? Can you see it now? Abi, it's your network. I think it's your network. Other people can see it. So, Kp, we consider gases only. Good. Now, let's come. I taught you here that, I said this here that it is product over reactant. That means I consider the product first before the reactant. Yeah, let's go. Now, product. Is there gas here? What is the gas here? What is the gas here? What is the gas here? Which one has a state that is gas? D, exactly. D is in gaseous state. So you write it like this. These two brackets, oh, you supposed to tell me that these two brackets means what? Don't ever forget. It means concentration. That two brackets means concentration. So D, now, the power, what is the coefficient of here is small letter d, you raise it to the power. Right? There's a coefficient. Now, will I write for C? Will I multiply by C? Will I multiply by C? Yes or no? Will I multiply this thing by C? Is it yes or no? Will I consider C? Should I consider C? No, you don't consider it. Thank you. C is in aqueous and this is pressure. We only consider gases. So I will not write for C. I will assume that it is 1. I will not write for C. I will assume that it is 1. I won't write for it. I won't write for C because it is in aqueous and they asked me to write for KP. That's the question 1. I will not write for C because it is in aqueous state. Don't forget that thing I said here. If you want to write for KP, we consider gases only. Gases only. So, and that's all for product. Reactant. Will I write for A? Yes or no? Will I write for A? Will I write for A? Will I write for A? The raised to power is what is here. Is the coefficient. It is the coefficient that you use. Every time you must always use the coefficient and raise to the power. Do you get? So yes, I will write for A. And what is the coefficient here? It has A. So I will put it here. Now the question is, will I write for B? Will I write for B? Yes, exactly. Will I write for B? Yes or no? Will I write for B? No, good. Jojo, good. Because it is in solid. We don't consider, I wrote it here. We don't consider solid and liquid. So this is the answer to that question. That's the answer. Number 2, let's go. KC or K. Let's go. Now, product over reactant. Product here. Will I write for C? Yes or no? Will I write for C? Will I write for C? Will I write for C? Yes, you guys are slow with the response. I will write for C because this is equilibrium constant for concentration. I will consider both. For concentration, we dissolved species. For concentration, we consider both gases and dissolved species. And C here is in aqueous, which is dissolved species. So I will write for C. The coefficient here is C. I will raise to the power. Now, please, this is another question that is very, very important. Will I write for D? Yes, because it is in gases. I have to consider it gases. But please note, it is multiplication, not addition. JAMB used to put addition here. It is multiplication. Then concentration of D raised to power D, that is here. All over the reactant, the only gas is here. There's no aqueous. So I will only pick this guy. I will only pick A raised to power what? A. So this is the answer to this question. So can you see? That's equilibrium constant for this. I will write for A because A is in gaseous. I will not write for B because it's in solid. So this is the answer to this question. Please never miss this question. It's a common JAMB question. I will even give you the one that JAMB asks you. I will give you the one that is inside JAMB pack. Now let's do another example. That one is in JAMB. This one is the one I want to give you now is a JAMB question. Now look at it. Consider this reaction. Why is it KC stroke? Good. Very good question. I told you that KC is equilibrium constant for concentration. K is equilibrium constant. The answer to these two of them is the same thing. If I have to write for K, I'm telling you to consider both gases and aqueous solution. If I have to write for KC, I'm considering both gases and aqueous solution. That's why I slash it. They are not the same thing. I just slash it to mean that they are the same when you are asked the question. That's why I just slash. So I don't want to confuse you. Precious, do you get that? Okay, now let's go. Now let's consider this. This is a JAMB question. Consider this. Consider this. Let's say we have Fe solid plus 4H2O gas to give Fe3O4 plus 4 hydrogen gas. This is a JAMB question. No? Now it's not balanced. 3 has to be here. Okay. Good. Now let's write the K, P, and KC, which is also K in this case, for the following reaction. Now, this is a JAMB question. This one, I didn't form it for my head. Yes, reversibility sign. Thank you. Must be there to show that they are in chemical equilibrium. It must be there. Let's go. Now, this is a JAMB question. This question is a JAMB question. Now, let's go. Now, another question, JAMB question. Fe3O4 is an ore of aluminum, which is magnetite. Just take note. Fe2O3 is the principal ore, which is hematite. Ore of aluminum is a JAMB question. I just have to say it here. So, no question. Hope you get that. Just scoop that. Magnetite is an ore. Fe, and this is the compound. Fe2O3 is an ore of iron, which is the principal ore, which is hematite. Now, let's write solution. Kp. Right? Now, I told you that we consider gases only. Yeah, let's come to the product. This is the only gas. It must be a balanced equation, though. You can see it is balanced. Fe here is 3. Hydrogen is 4. 4 times 2. Hydrogen is 8. 4 times 2, 8. 4 times 2, 8. Oxygen is 4. 4. Okay, it's balanced. Now, if you come to the product side, this guy is solid, and this is the only gas. So I will write H2. Then I will raise to power 4 the coefficient. All over product side, this guy is in gaseous state. I will write it. I'm not going to write this because I told you we don't consider solid when writing equilibrium constant. So it is 1. Then this guy, H2O, we JAMB give it the, yes, they gave it in the JAMB pack. Balanced. They gave it balanced. But you should know how to balance it too. Then H2O is raised to power what? Raised to power 4. Can you see? So this is the answer. You see that I did not pick solid because, yes, exactly. Thank you, Jojo Fat. I did not pick solid because I don't consider it. I did not pick this because it's solid. In fact, I can also tell you that Kp, Kc, or K is also the same thing because there's no aqueous. It's only gas. So I will just pick H2 raised to power 4 all over because solid, I don't consider it. The only gaseous here, there's no aqueous also. Then H2 raised to power 4. So the answer to the Kp or Kc or K for this particular reaction is the same thing. Sir, it's not clear. What is not clear there? What exactly is not clear? What exactly? You can't say it's not clear. You must tell me which one. Is it that I'm considering only gases? What is not clear? What is not clear? Please don't say it's not clear. What is not clear? I will remove one of you, not talk. But let me just say it again. If you want to write Kp, I already told you it is product over reactant. The second one is the same thing. We only consider gases and aqueous solution now. I told you that. But the question is, if you come here, is there aqueous solution? No. We only have gases. I only pick this guy. That's why I put it H2 raised to power 4. Solid lele is not in aqueous solution. So I will not pick it. It is 1. All over, I will come to the reactant. This is the only gaseous. There's no aqueous here. I only pick this guy. So that's why they are the same thing. Because there's no aqueous. If there had been aqueous here, this one would have been different. If there had been aqueous in this reaction, this one would have been different. Tilda, do you get that now? Do you get that? Do you guys get it? I mean, not Tilda. Okay, good. Super enjoying it. Good. Now, this one, the next thing I want to say now is in your JAMB pack. I can't see it clearly. I think your network is bad, though. You are the only one saying you can't see it clearly every time. I think your network is bad. Your network is bad. You can also revisit it anyways. Now, this one is in your JAMB question. K forward and K backward. Like equilibrium constant for forward reaction. Forward reaction. And equilibrium constant for backward reaction. This one is in your JAMB pack. Okay, K is equilibrium constant. K is equilibrium constant, but F means forward reaction and B means backward reaction. You will see something that will happen now. Look at it. Don't forget, let's say I have, look at this. Let's say I have A plus B to give C plus D. Do you know that there are two reactions here? Do you know that there are two reactions? This guy is the forward reaction. That is why it is two arrow. Why this guy is the backward reaction. See, pay attention. If you don't pay attention here, it will look like magic. Oh. Okay, that's that. Now, close your eyes and forget this arrow. You know, this arrow is coming from this side to this side. Close your eyes, and don't look at this arrow down. The arrow that is down, don't look at it. Just close your eyes. You know it is going like this. Why this one is coming from here and going like this? What is not showing very well? They are now two. Are you sure? Can everybody see this thing? Can everybody see it very well? I want to be sure it's not your network. Can everybody see it very well? I just want multiple people. Tilda, can you see it? John, can you see it? It's your network. It's your network. It is their network. Good. Good. It is their network. Get it. I can see it very clearly. Good, good, good. I think it's their network. Okay, good. Koide can see it. Good. But I can see it. Good. Okay, let's continue. Now, I said you should blur your eye. You guys should blur this guy and consider this. Now, let me ask you, if you blur this guy for this forward reaction, what is the reactant? What if you blur this down one? Don't look at it. Blur it. What is the reactant? If you are going like this, what is the reactant? Just tell me A and B or C or D. What is the reactant? It is important to. If you blur this guy, I already blur it for you. Don't look at this arrow. What is the reactant? A plus B, good. A and B, good, good, good. A and B, good. So, A and B, fantastic. What is the product for that arrow? What is the product? What is the product? That means let's A and B, good. That means for forward reaction, I know why I'm using this time to explain it to. Reactant is A and B. The product is C and D. Good guys, good guys. That's for forward reaction because I already blurred the backward reaction. Now, blur the forward reaction. Tilda, what is the reactant now? Blur the forward reaction. For this backward reaction, what is the reactant? I already blur it for you. Where is it coming from? It's coming from where to where? Blur the... Thank you. C and D is the reactant because it's coming from this side. Look at the arrow to this side. C and D becomes the reactant. A and B becomes the product. Thank you. You guys are amazing. Now, that means because there's a reason. It's not only C, it is C and D. For backward reaction, the reactant becomes C and D, and the product becomes A and B. Now let's write equilibrium constant for them. Now, K forward. I have to start from a new slate because if not, you will not get that. Let me pick a new book. Now, you guys should look something. Just be looking at it so that I want to be showing you the two. Now look at it. Let's start. For K forward, for the equilibrium constant for the forward reaction. K forward. I already told you that when you write equilibrium constant, it is always what? Product over reactant. Oh yeah, let's write. Let's write. Just consider everything to be gas, 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 gas. So now let's write K forward. What is the for the K forward reaction? What is the product? What is the product? Oh yeah, we already said it is C and D. I already told you it is C. It is not plus. It is always multiplication when writing equilibrium constant. Don't ever miss this one. If it's this thing that you know today, I'm okay. It is always multiplication, not addition. JAMB will put addition as option A. You go and miss it. They can either put multiplication or they put dots or they don't put anything. So they can write it in different ways. Over, what is the reactant? A and B. So they can either write it like this, A, then they write B. Okay, so this also means multiplication, but it is never addition. So it's either you see dots or you see multiplication or you don't see anything. These are the ways to show that it is multiplication. Good girls, good girls, good, good, good. Now let's go. K backward, there's a JAMB question. That's why I'm teaching it like this. Oh, for K backward, what did you say the product is? What did you say the product is? A and B are B. You guys already said it. So please, can you go for the Avogadro's law next? Thanks. What is Avogadro's law? Let's go. A, what is the backward reaction? A and B. I'm not teaching Avogadro, I'm teaching chemical equilibrium. It's not Avogadro's law. A and B is the what? Is the product for the backward reaction. A and B is the product for the backward reaction. I did not put anything now. It's not raised to power now. Can you see? There's not. It's just an hypothetical reaction. It's just an hypothetical reaction. I didn't put anything. If I put anything, it would have been raised to power. So don't worry. I know what I'm doing. I didn't put anything. So you already said this is the product, and it still always stands. Product over reactant. B. Good. All over, what is the reactant for the backward reaction? We already said it. It's coming from here to here. So C and D. C and D. Now, what is the JAMB question? The JAMB question says that the product of the backward reaction multiplied by forward reaction is equal to 1. This is the JAMB question. And that's what I want to prove now. The product of forward reaction and backward reaction is equal to 1. Or JAMB can say forward reaction, the equilibrium constant for forward reaction is a multiplicative inverse of the backward reaction. Or this is another way JAMB can put it. K forward equals to 1 over K backward. If you go to your past question, you see this question there. I kid you not. Now let's go. Why? How is it so? Let's write. K forward multiplied by K backward is like writing this guy. C into D all over A, B into B multiplied by this guy. A into B, because that's backward reaction, all over C into D. Because I know mathematics very well, it's easy. I just put this guy here, then this guy here. What do? This guy looks like this guy. This guy looks like this guy. Then K forward multiplied by K backward is equal to 1. It's always equal to 1. So this is a JAMB question. Do you guys get it? Do you guys get it? It is a JAMB question. So do you guys get it? Where does I'm seeing C and D? Oh, good. I think your network is lagging. Good. You guys got it. I'm happy. Let's solve one more. So this is a JAMB question. Please don't ever forget it. It's a JAMB question. This one is inside your past question. If you check. Okay. Now, let's solve one more. Then, yeah. So let's solve one more question on equilibrium constant. CaCO3 solid to give CaO solid plus CO2 gas is balanced. Absolutely. Calcium here is 1, calcium here is 1, carbon here is 1, carbon here is 1, oxygen is 3 here, 0 plus oxygen 1 here plus 2 oxygen here, that's 3. So this is a balanced equation. You are not adding any coefficient. So now let's go. Write Kp and Kc for the above reaction. It is very easy. Solution. Don't forget, Kp, what do we consider? Gases only. This is the only gas. So we just write it. CO2. That is product over reactant. This other product is not a gas, or is not a gas. We don't consider it. Now over reactant. The reactant is also solid. So this is the answer. So don't go and say, can the answer be CO2? Please prove the other Kb care. Kb. Sir, please prove the other Kb. What am I proving again? Prove the other Kb care. I already said it now. I explained even though little by little for this thing. Come on. I don't even know where it is again. Who is that? Sorry. Recap. Where should I recap? You guys are not following this thing. No. I don't even know where it is again. I even will explain little by little. K backward and K forward. Okay. Let's go. Now look at it. I said this arrow on top shows it is forward. This guy shows it is backward. And I said if you want to look for forward reaction, you blur out this down arrow so that you can know the reactant and the product. Now if you blur this arrow, you can see that A and B are the reactant. Then C and D are the product. Right? So A and B are the reactant, C and D are the product, because it's coming from here. These are the one reacting. These are the one colliding, forming C and D. So this A and B, for this forward reaction, A and B becomes the reactant, C and D becomes the product. That one that is K forward and equals and it's the same thing now. This is mathematics now. K forward times K backward equals to 1. So divide both sides by KB. That's 1 over KB equals to K forward now. K backward, this means K backward. I already wrote it now. If you write K forward as this, K backward as this, multiply the two together, you will see that C and D and A and B, we can cancel this guy like this. Then this one will cancel this. Then this, everything becomes 1. Then from here I can say K forward equals to 1 over KB2. So the question in JAMB is that K forward is a multiplicative inverse of K backward. That's it. It's not hard. There's no pressure there. So that's that. So let's move on, please. There's no time. Are you good now? Can I move on? Okay, now look at it. K, we already said we consider gases only. Gases only for KP. Gases only. Now this CO2 is the only gas. So it's only one I'm picking. Solid, nothing. Number 2. So this is the answer. Kc or K, I already told you can use K2. Kc or K. Now it's still product over reactant. And I told you that for Kp or K, we consider gases and aqueous solution or dissolved species. Now this is the only gas, CO2. All over product, CaCO3. CaCO3 is solid. CaO is solid. We don't consider solid and liquid. I already told you. So this is the answer to the two questions. So either ways that they ask you this question, this is the answer. Are we good? Are we good with that? Only one person that is good with it. I want to respond. So before I move to another concept, the second JAMB question. Which one is the second JAMB question again? Please don't move. I think your network is bad. I mean, not. You might want to come back to watch it. I don't know. Your network is bad. Is it this one? Your network is bad. I don't want it should not be too long. That's the idea. Now, I think your network, because I explained it so basic and I don't know. I think your network is bad. So now we want to get to factors affecting the position of equilibrium constant. You know, we already established equilibrium constants, and so factors affecting the position of equilibrium constant. Do you mean I should re-explain this? I'm hearing yes, sir, yes, sir. Do you mean we should go to the factors, or I should re-explain that? Oh yeah, oh yeah. Which one do you want to, before I move on? Factors. The TCP, that's my TCP. Temperature, concentration, and pressure. Which one do you want? Is it that we should go to factors now? Move forward. Okay, good. Oh yeah, let's go. Move on. Okay, good. I'm fine now. Now let's go. Factors, good. I have understood. You've understood. You've understood. Have is an anomalous verb. There are three anomalous verbs: as, have, had. Has is singular. Have is plural. Then had is the past tense of the two. So anytime you use these guys, right, they are called anomalous verb. Anomalous. They behave abnormally. You must use their past participle with them. Past participle. So you say she has gone. She has gone. Gone is the past participle of go. You understand? She has come. She has come. You understand? They, because it is plural, they have gone. They have gone. Okay? You still oh, you don't know. I know there's nothing I cannot teach you now. Oh, you think sin happens? Anyways, that's by the way. Hope you know that you got this of anomalous. Anomalous verbs. Unusual. They behave abnormally. So that let's go. Now boss, you know easy. So please take note of this. Oh, anytime you use this verb, so it's not have understand, it's have understood. Understood is the past participle of understand. Do you get? So let's leave this. You guys should not whine me. Yeah, let's continue. I just have to say that in case you don't know, they ask this question very well in JAMB. So let's go. Like, what is better is that I know most of the questions that they ask in JAMB. I mean, I did JAMB 3 times and it's not easy. Okay, let's go. Factors. that affect the position of equilibrium constant. We'll leave that one, leave that one, leave that one. Don't worry. That's another day. Okay, now let's go. Yes, I gave you textbooks. Exactly. Thank you, Jerry. You have been reading it. Yeah, you have been reading it. It shows that you have been reading it. I will fail me. Thank you, Jerry. Thank you. Some people are not reading that textbook. Okay. Now, they are just TCP. What do I mean? They are just three factors that affect the position of equilibrium constant. They are just three factors that affect the position of equilibrium constant. What are they? T, which means temperature. C means concentration. And P means pressure. These are just the factors. Good, John. Thank you for reading it. Bless up. These are just the factors. Now, before we delve into this thing, please, JAMB question. Which of the following is not a factor that affects equilibrium constant? A, temperature. B, concentration. C, pressure. D, catalyst. Please, catalyst does not affect equilibrium constant, but it can affect the rate of forward reaction. Please don't say anything on the comments aside as regards what we are, that is not related with what we are doing. Please, I want us to finish on time. The time is going. Just focus on this thing for now, please. Now, temperature, concentration, and pressure are the only. No, I know what you are talking about temperature. Don't worry, I know I will get there. TCP are the ones that affect equilibrium constant, right? The position of equilibrium constant, right? Why temperature is the only factor that affects the magnitude of equilibrium constant. Okay, now let's get into it. But there's a particular man that made this thing very interesting, and that man is called Leo Chatelier's. I don't know why people cram this in. Leo Chatelier's principle. I will tell you, he's a French guy, so we call it Leo Chatelier's principle. Now, what does this man say? And I will explain. Tilda, I want to ask you a question. If you mistakenly add too much salt to your food, what would you do to correct it? Are you on? What are you saying? Jojo, what did I say again? Don't worry, just know TCP. It's TCP that I just said. All this thing I said before is not related. It's related, but I've not gotten there. I will still get there. Just know that these are the factors. Factors are TCP. It's a way to know it. You had it. Thank you. Baker cooks. You see how Baker, because she cooks, I think that's her name. You add enough water. Do you know why you add enough water? You want to correct the effect that too much salt has caused. That's what this guy is saying. Now let's come back to chemistry. You said you add water because of too much salt, right? To correct the effect that too much salt has caused. Now what does this law say? He said that if any of the factors keeping a reaction in equilibrium is affected. What are the factors that he's talking about? See, temperature, concentration, and pressure. That is, he said, if any of these factors, if that is just conventional, it might not ruin the food. What will you now do? What will you do? But see, I don't want to divert too much, but I just want to get the concept is that you want to add too much water, or you want to add water, not too much water, add water to correct it. That's just the idea. If any of the factors keeping a reaction in equilibrium, what are the factors we are talking about? TCP is affected. The equilibrium position will shift in order to annul or cancel the effect of change. See, you don't need to cram this thing. You don't need to cram it at all. It is one of the easiest thing you will see. It's just the case of your rice, your too much salt. You know that the salt will keep the food okay, but that you've already add too much, too much salt. You want, so the what will happen is that adding water, we try to alter, we try to make to shift it, so that that effect, that change, that that too much salt will be cancelled. So that's what this law is saying. It said if any of the factors keeping a reaction in equilibrium, what are these factors? TCP, that is, if you increase temperature or you decrease temperature, if you increase pressure or you decrease pressure, if you increase concentration or you decrease concentration, that's what you are trying to say here, is affected. The equilibrium position, the position will shift in order to annul. The word annul means to cancel, or cancel the effect that has caused by that change in the factors. Do you get that law now? Do you guys get the law now? So I don't want you to cram this law. Okay, I don't want you to cram it at all. Do you guys get it? Yes or no? Yes or no? Good. Now let's not go into it. Good. Good. Screenshot if you want to screenshot. Yes, good. Now, okay, now let's start with the number one. Hey, you can come back to watch it though. I think that person just joined. I don't know. Number one, temperature, because I explained it so much. Temperature. Now, before you can talk about effect of temperature, the first thing you want to know is types of thermodynamic. No, it's not. It's thermochemical reaction. Thermochemical reaction. Types of thermochemical reaction. There are just two. Do you know why? Because you cannot know the effect of temperature on a reaction unless you know the enthalpy state of that reaction. And that's why you have to understand the types. Number one, exothermic reaction. I will explain exothermic reaction and endothermic. So let me just explain exothermic like that. Or should I write it? No, let me write. The word exo here means exit. This is temperature. So exothermic reaction is the release, just like exit, or let me, so that you don't forget, exit of heat to the surroundings. Just like the word exit, exit, release. Now, don't forget that this means enthalpy change, not entropy. Enthalpy change. Enthalpy change, or sometimes we call it heat content, like the heat content. So for exothermic reaction, the enthalpy change is negative. You must know this, because this is what will determine the effect of temperature on that reaction. That's why I used to say that most examiners, they will always give you the enthalpy change of that reaction, so that you can determine the effect of temperature of that on that reaction. If they don't give you this, you will not know. You will see it by the time we start. So that is number one. Number two, endothermic reaction. Now, what is endo? Just like the name, endo, inside. Endo, inside. So it is the absorption of heat. Absorption, endo, inside. Inside. Absorption of heat from the surrounding. Absorption of heat from the surroundings. Now, in this case, the change in H is positive. The change in H is positive. The change in H is positive. You must always know this. The change in H is positive. Now also, because this is exam is fast approaching, you must also know the curve, the energy profile of these two things. You must also know the energy profile of these two things. Now, how do you know it? How do you know it? It's easy. So for exothermic, because we already said that the change in H is negative. Now look at how it's going to happen. If you have the energy profile like this, look at it. Look at what will happen. This is the reactant. This here is the activation energy. Don't forget, activation energy is the minimum energy. Is the minimum energy. Please take note of that. Needed for a reactant to form the product. Don't forget, is the minimum energy. JAMB question. Is the minimum energy needed for the reactant to form the product. That means if this reactant did not have an energy equal or greater than activation energy, it will not jump to this side. That's what it means. Now, that's by the way. Now, if you trace it, you see that this is HR. If you trace this, you see that this is HP. Now, let's give a value to it. Let's give a value 0, 2, 4. Now, let's do. Don't forget, the change in H will be HP minus HR. Absolutely. Now, if you trace this guy, you can see that this HP is 2 minus HR is 4. So this is what they call energy profile. So 2 minus 4 is what? Minus 2. So that is why change in H for exothermic is negative. So this now that is mathematical way to know exothermic. But me, I have a logical way. You know, it is exo. So the product side will exit. That's the way I know it. Look at it. Look at the product side. You can see the arm of the product side is exiting. Is greater than this one. So that's the way I know it. From here, since it's exothermic, it will exit. Exiting. So that's the logical way to know it. Do you guys get that? But for endothermic, you see that the product side will be shorter. Do you guys get that? Do you guys get that? Only one person. Good. Let's go to endothermic. Because you need that for your exam. That's why I have to say it. Now look at the way the graph will be. You will see endo. This one will be short. The product will be short. That's why I know it. Logical way, no. I will not use mathematical way. Now trace this guy like this. Trace this guy like this. How come the 4 and 2, sir? It's just a number. How come? It's just a number. I just put a number there. It's just a number. Nothing, no specialty. I'm just trying to tell you that any number that is here will be lesser than here. So if you do it, 2 minus 4 will be minus. That's what I just did. I can put 100 and anything there. It's just a number to denote. Oh yeah, screenshot. If you cannot meet up, screenshot. Do you get that now? Okay. Now, I just put another number. You can see. But don't forget that it must go like this. Order, increasing order. This one will be 6. Normal graph. Like that. So, let's go. Change in H will be what? HP minus HR. And me looking at it, you see that HP is what? Is 4. Minus HR is what? Is 2. So, what do you observe? 4 minus 2 is what? positive, positive, positive 2, positive 2. So that is why the enthalpy change of an endothermic reaction is positive, based on what I just explained. So this is a JAMB question. Another JAMB question is that this thing can be catalyzed. This is another JAMB question. Oh. So because catalyst lowers the activation energy, that's the effect of catalyst on the reaction. It lowers the activation energy. So this is called catalyzed pathway. This is a JAMB question. Catalyzed path. And this one that is I is called uncatalyzed path. I just have to say it because it's a JAMB question. So this catalyzed path, because you can see that the activation energy is reduced. So don't ever forget it. The effect of catalyst on activation energy. Effect of catalyst. This one is by the way. Oh. Please don't go and think it's the same. It's not part of the thing. Oh. I just have to say it because of the exam. Effect of catalyst is to lower or reduce the activation energy. This is a JAMB question. They asked me in all my 3 JAMB that I ever wrote. They asked me this question. So that's why I have to say it. Please take note of that. So now let's move on. Now that we know this change in age of a thing, now let's now do a particular equation and use it to explain everything. Now look at what will happen. If you are writing screenshot, there's no time. Okay. Now let's go. Now let's see something. Look at what will happen. Consider this reaction. A plus B to give C plus D, given that the change in H is negative. Now, question 1. What is the effect of 1, increase in temperature? That's why I told you. You see why we have to go through those things we did. Number 2, decrease in temperature. Sir, please, the other speed, I want to screenshot. Okay. Oh yeah, screenshot. Done. I expect it to be done. Now, solution. It should be done now. Okay, good. Yeah, you're welcome. Now, solution. Now, let me ask you a question. You already see this negative. What does it mean? What does this reaction mean? Before we go to solution, what does it mean? What does it mean? Because exothermic reaction. Good. Jojo said exothermic reaction. Now, good. Now, the reaction, that's why you cannot know that this reaction is exothermic unless they give you this thing. You see why it is important? Unless they give you this, you cannot know that it's exothermic unless they give you. So that is why it is important that you know this particular thing. Now, because we know that it is an exothermic reaction, now that's the first statement. It is an exothermic reaction. That means by default, it's already releasing heat. Now, I will ask you a question. It's already releasing heat. Now, if you want to help this guy, do you think you should increase the temperature? Like, do you think increasing the temperature will help this guy to move forward? That's the question. Do you think increasing the temperature will help this guy to move forward? Because the reaction is already releasing heat. Do you think when I increase the temperature, it will favor forward reaction? Do you think it will favor forward reaction? If you increase the temperature of a reaction that is normally releasing heat, do you think, no, decrease, thank you very much. No, it will not favor. Good guys. So that is it. So number 1, increase in temperature, because the reaction is already releasing heat, increase in temperature will favor backward reaction. It will not allow you to move forward. It will favor backward reaction because the forward reaction is already releasing heat. So the only way you can favor is to favor backward, because by default, if the forward reaction is exothermic, the backward reaction will be endothermic. That's the meaning. That's the meaning. That's no, don't think it too much. Once the forward reaction like this is exothermic, the backward is endothermic. If the forward is endothermic, the backward is exothermic. So it will favor backward reaction because this reaction is already, it's just like you have enough money. Why should I give you money? Because you have enough money so that you are even releasing it. So you have enough heat so that you are even letting it go out. Why should I give you heat again? So that is why you must know this, that it will favor what? Forward. It will favor backward reaction if you increase the temperature, because the reaction itself is releasing heat. Increase reaction or decrease. What's increase reaction? Increase in temperature for this reaction will favor backward reaction. It will favor backward reaction. Number 2, what is the effect of decrease in temperature? Absolutely, that's what this guy wants. That's what he wanted. That's what he wanted, because the reaction is exothermic, is releasing heat. How can you favor it? Is to help the guy to collect the heat. So decrease in temperature we favor forward reaction. We favor forward reaction. We favor forward reaction. Exactly. Thank you. Do you guys get it now? Do you guys get it? Do you guys get it? I will just use another example then. That's all about that. Understood? Fantastic, guys. Fantastic. You guys are amazing. Yes, sir. Good. So screenshot if you want to. Please come again, sir. Kabaya. From where? Where exactly? But anyways, the reaction is exothermic. It is releasing heat. Now, if you increase the temperature of a reaction that is normally releasing heat, you are not favoring it. You are not favoring forward reaction. So you favor backward reaction because the reaction itself is releasing heat. Number 2, decrease in temperature. Because the reaction is releasing heat, the only way you can favor it is to decrease the temperature. Because why should you be giving increase in temperature? Okay, I already explained it. Increase in temperature will favor backward reaction. It will not favor forward because the reaction normally is releasing heat. So increase in temperature will not favor forward. It will favor backward reaction. So Olushola, do you get that? Now let's use another example to explain that. Let's say you have A plus B to give C. Then argue that change in H is positive. Now, number 1, what is the effect of increase in temperature? Number 2, I will not write this one. What is the effect of decrease in temperature? I will just explain with the mouth. I need to screenshot, sure. Yeah, do that now. Do that now. Good. Now let's go. Now, since the reaction, this enthalpy change is positive, it means the reaction is what? Endothermic, which means this reaction needs to absorb heat. It needs to absorb heat. That's what it means. The reaction needs to absorb heat. So now, I mean, if you increase the temperature, what will you do? You are helping it because the reaction needs to absorb heat. So increase in temperature favors forward reaction because the reaction needs heat. The reaction itself is absorbing heat. So when you increase the temperature, you favor forward reaction. Yes. Then number 2, decrease in temperature. A reaction that is absorbing heat, you are not decreasing the temperature. You have caused wala. You are favoring its backwardness. You are favoring backward reaction. Do you guys get it now? It's not hard. Do you guys get it? Do you guys get it? Yes, good. Now, there's something I must tell you here. Good. There's no time. Now, there's something I must tell you here. Increase in temperature for yes, because it's an endothermic reaction. There's something I must tell you here. You know, we already said that TCP are the factors that affect, the position of equilibrium constant. But look at this. This OAU question, positive question, but you can know it. It is only temperature that can change the magnitude. The word magnitude means or size of equilibrium constant. You should know this one. I will tell you, you will see it now. Yes, TCP is they are the one for positions, all of them. But it is only temperature that can change the magnitude. That was what one guy said the other time. Or size. Now how? There's a relationship called Kp equals to Kc RT change in N. So now look at it. This equilibrium constant for partial pressure. This equilibrium constant for concentration. It is not pressure and concentration. It is equilibrium constant for pressure and concentration. Now this is gas constant R, and this is temperature. So it's only temperature that is in between here. There's no pressure here. There's no concentration here. It's just Kc, which is not concentration. This Kp is not pressure, but temperature as a factor is here. That is why temperature is the only factor that can change the magnitude, Oye, or size of equilibrium constant. This question, if you are doing OAU post TME, you should know it. It's a question, common question in OAU post TME. Okay, it's a common question in OAU post TME. So this is that. Note this, screenshot it if you want. Now this change in N, you should know it, is NP minus NR. NP minus NR, like number of moles of the product over number of moles of the reactant. Number of moles of the product over number of moles of the reactant. Okay, now let's continue. Now let's go to the next one. The next one is, we say TCP, concentration. This one is straightforward. I mean, if you have A and B to give C and D, this one is straightforward. It's as simple as ABC. If you want more of the product, what do? You increase reactant. So high concentration of A and B will favor forward reaction. Like increase in concentration of A and B will favor forward reaction. It's just simple. If you are making eba and your mommy tell you to go and make more eba, what do? You increase the concentration of the garri and the concentration of the water so that you can make more eba. So that is it. Garri and water, they are the reactants to form eba. So if you want more eba, you increase this one to get more eba. So the higher the concentration of the reactant, it favors the forward reaction. If you increase the concentration of the product, it favors the backward reaction. If you decrease the concentration of the product reactant, it decrease. This one decrease, and it favors backward reaction. It will not favor forward. Once you decrease this guy, it will favor backward, not forward. Please, endothermic. I've explained that. You can watch it after this time. I've gone away from an endothermic reaction. So now, as I said, that increase in concentration of the reactant will favor forward reaction. If you decrease this one, it will favor backward. If you increase this, it will favor forward. If you decrease it, it will favor forward. To screenshot. Okay. Please always screenshot on time. Oh yeah, screenshot. We've used 1 hour, almost 40 minutes now. It should not take us this time. Now let's go. Now the one that is not inside your textbook is constant removal of the product will favor forward reaction. This one is very simple that you must know it. I mean, if you react A plus B to form C, if you constantly remove A and A, if you constantly, this is the product, we already know, and this is the reactant. If you constantly remove C, C, eventually you will exhaust A and B. You don't care because you just want to form more of C. So constant removal of the product will favor forward reaction. Eventually you have more of C and you will exhaust A and B. So constant removal of the product will favor forward reaction. The way I used to explain this thing, if you are in a party and someone is sitting there in a place and constantly taking more of the takeaway pack, I don't get, please. If you constantly remove C, you have more of C and exhaust A and B. So if you have more of C, it means you are favoring forward reaction. You are favoring forward reaction because you have more of C. That's just it. It's not hard. So if you're in a party and someone sitting down somewhere and constantly taking the takeaway pack, eventually that person will have more of the takeaway pack because it's constantly removing it, keeping it. Eventually the takeaway can finish, but the person will have more of the takeaway. The same thing is happening. A and B is forming C, but if you constantly remove C, eventually A and B will finish now, but you have more of C. These are C. This is C that you are seeing here. C will be plenty, but A and B can finish. So it will favor forward reaction because you are forming more of C, which is the product. Do you guys get it? Do you guys get it? Do you guys get it? Before we move to pressure, which is the last one. Good. Let's go to the last one, the last but not the least, which is pressure. If you have not screenshotted, please do so now. Screenshot. Sir, can you please come again with the concentration? Hey, this stuff is too long. A and B, right? A and B is forming C and D. How do you form more of C and D? Increase A and B, you form C and D. You form more. So increase in the reactant will result to increase in the product, favoring the forward. If you increase product, you favor backward. That is, more of the reactants will be formed. That's just it. And I use a trivial example. If you want to make more eba, increase garri and increase the water. That's what I just said. So eba is the product. How do you form more eba? Increase garri, increase water. Now those are just basic ways to know it. But this one is important because if you constant removal of the product will favor forward reaction. How? If you constantly remove C, this is the product. Eventually you have more of C. Can you see? C becomes, you have a lot of C. But this one can exhaust it. This one can finish. You don't care. But the product will keep forming more. So that's what I said. I think that's so explanatory now. Don't always forget, pressure only affects gases. Don't always forget it. Pressure only affects gases. So now let's go. This is the effect you are seeing here uses the principle of Boyle's law, but that's not where we are going to. I just want you to know that it uses the principle of what? Boyle's law. Principle of Boyle's law. Very important that you know that. Now let's go. This one is a JAMB question. N2 plus hydrogen gas to give ammonia. Please note, this is ABBA process. This is what they call ABBA process. ABBA process. Ratio 1 to 3 to 2. When you produce ammonia gas, it is called Haber process. This is a JAMB question. Haber process, okay? In ratio 1 to 3 to 2. Now, they are all gases. That means pressure can affect them. So now, let's look. What is the effect of increase in pressure? Please pay attention. If you don't pay attention. 2. Decrease in pressure. Okay. Now, let's go. Now, look at this reaction. From this, what can you tell me? This is 1 mole of this guy plus of this guy to give 2 moles of product. That's what you can see here. 2, this is 2. Haber process, yes, I've said it. Haber. Then this is 3. What is here? Then 1. So eventually, what is the total mole? 4 moles of reactant. It's important that you know this thing I'm doing, and 2 moles of product. Now, don't forget, Avogadro's law has made us to be able to convert mole to volume. And that's why Avogadro's law is N is directly proportional to volume. That's what it states. N is directly proportional to volume. Now, from here, I can say this 4 mole means 4 volumes, then 2 volumes. It's just converting what the mole to volume. 2 moles, 4 volumes. That's all. Now, let's go. Increase in pressure. I said that we are using Boyle's law. In increase in concentration of the reactant, we favor what? It will favor forward now. Reactant is not what you are, is what you are reacting together. Eventually, you have more of the product. You guys, it's simple now. If you want to make more eba, what do? Increase the reactant. Garri and water are the reactant. Increase the reactant to make more eba. Eba is the product. Now, you guys should pay attention, please. Now, 4 volumes and 2 volumes, right? Now, I told you that this principle follows Boyle's law. Boyle's law said that pressure is inversely proportional to volume, right? Now, look at it. The question is, increase in pressure will go to lower volume. Don't forget, I said that pressure, Boyle's law is pressure is inversely proportional to volume. So if you increase the pressure, between 4 and 2, which one is low? Between 4 and 2, which one is low? Which one is low between 4 and 2? Are you sure you are still here? Two, yes. So number 1 case, increase in pressure. Increase in pressure, because according to Boyle's law, it states that pressure is inversely proportional to volume. So increase in pressure we go to what? Lower volume. Not volt, volume new. It's not volt, it's volume. Volumes. So increase in pressure we go to lower, and this is 2. And that is the product side. It is 2, and that's the product side. So increase in pressure in this case, we favor forward reaction. Number 2, decrease in pressure. According to the Boyle's law, pressure is inversely proportional to volume. Pressure is inversely proportional to volume. So if you have decrease in pressure, where do you think, which volume will it go? Is it higher volume or lower volume? Since there's a decrease in pressure, will it go to higher volume or lower volume? Decrease in pressure, according to this law, will it go to lower volume or higher volume? Lower volume or higher volume? Decrease in pressure. Decrease in pressure. Will it go to lower volume or higher volume? Why will it go to lower when it's already decreased? It will go to higher now. When it's already decreased, it cannot go to lower. You are saying that pressure is directly proportional to volume like that. But we said pressure is inversely, which means when pressure increases, volume must decrease. When pressure decrease, volume must increase. That's it. So it will go to, thank you, it will go to higher volumes. And it is this 4 that is the highest volume. So it favor the reactant side, or I can say it favor backward reaction, because that's the reactant side. It favor, so that's the principle. Just know that. That is why one of the conditions in Haber process, because I want formation of ammonia to be many, it is increase in pressure. That if you go and read your textbook now, you will see it. It is increase in pressure that makes it to form more of ammonia. So because it will favor forward reaction. So this is one of the conditions in Haber process. Another condition is temperature. Another condition is catalyst. Another condition is catalyst. So I can't hear you again. It's your network. Ah, God. I think you come and watch it again. I think I'm tired. I have to finish it before. You come and watch it again. But let me say it again. If you don't get it now, you have to watch it again. Increase in pressure, we go to lower volume. That's what Boyle's law states. It's the network. It's not my fault. Can you see now? And you are stressing me. Ah, God, I'm tired. So, pressure, increase in pressure, lower volume, right? So, increase in pressure, we go to lower volume. Can you see? 2. That's where the lower volume, and that is the product side. That is the product side. So, it will favor forward reaction. Decrease in pressure, we favor higher volume, and that is the reactant side. It favor the backward reaction or reactant side. Okay, that's that. Another thing you have to know, this is not part, please. Sir, I can't hear you, sir. Your network, oh. Can everybody hear me? This is another JAMB question. This is another JAMB question. What is the effect of pressure? Who can tell me what is the effect of pressure on this reaction? What is the effect of pressure on this reaction? No effect, because it is equal. Those are the people that have read. Exactly. There will be no effect because it is equal. Why? Look at it. N2 gas plus O2 gas. It will be 2NO gas. This is 1 to 1. It is balanced like this because N2 here is, N here is 2, N here is 2. Oxygen is 2, oxygen is 2. So 1 to 1. That means 1 plus 1 is equals to 2 volumes to give 2 volumes. So regardless of either you increase pressure or you decrease pressure, no effect because their volumes are the same. No effect. This is a JAMB question. No effect. No effect. No effect. And another way that you can have no effect is the same thing, just like you have here, is when changing N equals to 0. Because I already told that change in N is NP minus NR. Just like you can see. What's the number of mole of the reactant? 2. Just put 2 here. What's the number of moles of the product? 2. 2 minus 2. So change in N equals to 0. In that case, there will be no effect. There will be no effect. There will be no effect. Oh my God. Let me see. I think, yes, that's the end of chemical equilibrium. I hope you enjoyed it. That's the end of chemical equilibrium. That's the end of chemical equilibrium. So, I hope you guys enjoyed it. That's the end of chemical equilibrium. That's the end of chemical equilibrium. So, I'm trying to form some set of questions. Set of questions now. Please, sir, the question, I didn't read it. Set of questions. We love you, sir. I love you too, guys. I love you. Set of questions. Just one, anyway. There's no... if you have A plus B I'm coming. Oh. I'll give you the question. Just one is okay. So give C. And the enthalpy change is positive. What is the effect? Amen, amen, amen. So since you guys screenshot if you want to. So this is the question. I never was that when you are doing. Yeah, you can watch it again. What is the effect of one increase in, just screenshot this and answer and come back to answer it in the comment section, and decrease in temperature. You don't need to watch it again or just answer it in the comment section. Just screenshot it. The change in H is positive. Oh. Just answer it. Oh yeah, answer it. Okay, so no, like what is the effect of increase in temperature, decrease in temperature? Screenshot it and come and answer it later. And drop it in the comment. Do you guys get that now? Screenshot it and come and answer it later. That means it shows that this thing is an endothermic reaction. So you now think, I don't know the answer, just come and drop it later in the comment section. I don't know the answer, just come and drop it. Don't worry. I will check the answer. Those are correct. So, yes. So, all right. I'm tired. I need to go now, guys. I need to go and eat and find something to eat. So, you come and drop the answer later in the comment section. Just screenshot it. Once I end this live, you come and drop the answer in the comment section. Okay? Do you get Ajibola, Precious, John, Tilda is still here, Folarin, Becca. So you come and drop the answer in the comment section. So screenshot it. Please show concentration. Where is it, sir? I can't even see concentration. This concentration. Just screenshot it, please. Screenshot it. I'll come and watch it later. I have to go now. My head is. Yeah, thank you, Precious. God bless you too. Thank you. So thank you so much. I hope you guys enjoyed it. I hope you're able to make good use of these things. They are not far-fetched. They are simple. So drop the answer. You would later come back to drop the answer in the comment section. I'm not checking your answer now. I don't know if you are correct. You come and drop it in the comment section. I need to go. My voice. I almost lost my voice. So guys, catch you guys later. I love you guys so much. Catch you. I need to go now. How do I even end this thing? You are too good. Thank you. Thank you. Becca, so drop in money in the reaction. Or multi say, I know that I'm tired. In the comment section. I think the biologic. Okay, let me just end this. So if you're just watching this, drop in the comment section, drop your answer. If this is an endothermic reaction, increase in temperature and decrease in temperature, what will be the effect? So guys, bye.